Chapter 12, Nervous Tissue, Electrical Signals in Neurons. Excitable cells communicate with each other by action potentials or graded potentials. Action potentials allow communication over short and long distances, whereas graded potentials allow communication over short distances only. Production of both types of potentials, action potentials and graded potentials, depends upon the existing of a resting membrane potential and the presence of certain types of ion channels. The membrane potential is a measure of the electrical voltage across the membrane. Graded and action potentials occur because ion channels in the membrane allow ion movement across the membrane that can change the membrane potential. This 3D physiology is a great video for you to watch. We have two basic types of ion channels in neurons. They are leakage or non-gated channels and gated channels. There are three types of gated channels: voltage, ligand, and mechanically. Leakage or non-gated channels will alternate between being open and closed. Here the channel is open, here it is closed. There will be more potassium channels than there are sodium channels. The gated channels, here we have the voltage gated channel, and they respond to voltage changes. So this is a direct change in membrane potential, because remember, the membrane potential is an electrical voltage or a charge across the membrane. Here we see the voltage is negative 70 millivolts and the channel is closed. When the voltage becomes less negative, then the channel opens. Ligand-gated channels respond to a specific chemical stimulus, such as a ligand binding to the receptor to either open or close the gate. Mechanically gated channels will respond to mechanical vibration or pressure stimuli. Here is a summary of the descriptions and locations of the different ion channels. Next is resting membrane potential. You will want to make sure that you understand resting membrane potential. The membrane of a non-conducting neuron is positive outside and negative inside. The membrane of a non-conducting neuron is positive outside and negative inside. This is due to the distribution of ions across the membrane and the relative permeability of the membrane towards sodium and potassium. A typical normal value for the resting membrane potential is negative 7 millivolts, and the membrane is said to be polarized. Resting membrane potential is determined by several factors. 1. The unequal distribution of ions across the plasma membrane and selective permeability of the membrane to sodium and potassium. 2. Most anions cannot leave the inside of the cell. And third, The sodium-potassium pumps compensate for the slow leakage of sodium into the cell by pumping it back out. So here we're showing these three factors. The unequal distribution of mainly sodium and potassium ions, sodium in the extracellular fluid, potassium in the intracellular fluid mainly, and that anions cannot leave the interior of the cell. And then the sodium-potassium pump here, compensating for the slow leakage of sodium into the cell and then pumping it back out. A graded potential is a small deviation from the resting membrane potential, resulting in the membrane becoming either more polarized, hyperpolarization, and more negative in its electrical voltage, or less polarized, depolarization, and less negative in electrical voltage. We see the electrical voltage measured on the y-axis and time on the x-axis. Graded potentials occur most often in the dendrites and cell body of a neuron. They occur as the result of the opening of a ligand-gated or mechanically gated channel. The signals will vary in amplitude or size depending on the strength of the stimulus, thus giving us the term graded potential or graded. We can take these graded potentials and then sum them together to create larger membrane voltage values. So here we see this summation, adding multiple graded potentials together to create a larger amplitude. An action potential or an impulse or an action potential or an impulse is going to be a sequence of rapidly occurring events that decrease and then eventually reverses the membrane potential. This process is called depolarization, and then it will restore it to the resting state or repolarize. During an action potential, we'll have the voltage-gated sodium and potassium channels open in sequence. So here you can see we start with the voltage-gated sodium channels opening, and that's going to cause us to depolarize. And then we'll have our voltage-gated potassium channels open while the sodium channels have closed. And then finally, the potassium channels will still be open and the sodium channels are in their resting state. First, we'll have this rapid opening of the voltage-gated sodium channels, as we said, causing the depolarization. If depolarization reaches threshold, then the membrane potential will reverse, and depolarization will occur due to the interaction of the two voltage-gated sodium channel gates, an activation gate and an inactivation gate. Next, the slower opening of the voltage-gated potassium channels and the closing of the previously open sodium channels leads to this repolarization and then the recovery of our resting membrane potential. Different stimulus strength will affect action potential generation. A subthreshold stimulus does not generate an action potential because we do not reach threshold. So therefore, subthreshold stimulus. By reaching threshold, we can generate an action potential. And then a suprathreshold stimuli generates an action potential, and oftentimes actually more than one action potential. During the refractory period, another impulse cannot be generated during the absolute refractory period. However, during relative refractory, if we have supra-threshold stimuli, then we can have another action potential generated. So during absolute refractory, no more action potentials can be generated, but during relative refractory period, we may have supra threshold stimuli generating more than one action potential. This just walks us through the action potential and sodium and potassium voltage gated channels once again. This table gives you a comparison of graded and action potentials. How do your action potentials move or travel from point to point along the membrane? In order for us to have communication from one body part to another, the action potential must travel from where they arise at the trigger zone to the axon terminals. This traveling action potential is called a nerve impulse. Action potentials do not die out. They will keep their strength as they spread across the membrane of the neuron. Local anesthetics and certain neurotoxins can prevent the opening of the voltage-gated channels so that nerve impulses cannot pass through the obstructed region. This step-by-step depolarization of each adjacent area of the plasma membrane is called continuous conduction. So here we show continuous versus saltatory conduction. And so in the continuous conduction, we have step-by-step depolarization occurring, and in the saltatory conduction, our nerve impulse must jump from neurofibril node to node. Remember, these are our nodes of Ranvier. And so what type of axons, by having these nodes of Ranvier, are these neurons? Propagation speed of a nerve impulse is not related actually to the strength of the stimulus. It is related to the diameter of the axon, the amount of myelination on the axon, and the temperature. Larger diameter fibers can conduct faster impulses than those with smaller diameters. Myelinated fibers, of course, can conduct impulses faster than unmyelinated fibers. And finally, nerve fibers conduct impulses faster when warmed and slower when cooled. Neurons will then be classified by diameter and myelination, therefore their conduction speed.